From the smallest subatomic particles to the grandest galaxies, our universe is in a constant state of motion. Understanding motion is fundamental to grasping the very fabric of the cosmos. Join me as we navigate the intricate dance of objects in motion, from the familiar to the cosmic. Imagine a single leaf falling from a tree, twirling in the breeze. This is motion in its simplest form, a change in position over time. But motion, like our universe, is rarely that simple. It's a tapestry woven from distance, displacement, speed, velocity, and acceleration. Distance is the total ground covered by our leaf. Displacement speaks of the shortest path between the leaf's starting point and its final resting place. Motion, like the universe itself, is full of diversity. It's the graceful arc of a ball thrown across a field, known as translational motion. Motion can also be rotational, like the spin of a planet on its axis. And let's not forget oscillatory motion, the back-and-forth rhythm of a pendulum. Each type of motion is a unique expression of the fundamental forces shaping our universe. Imagine yourself on a journey, a winding road stretching out before you. The odometer in your car records every mile, every twist and turn along your path. That is distance, the total path traversed. Now picture a straight line connecting your starting point to your final destination. This is displacement, the shortest path between 2 points. Distance and displacement, two sides of the same coin, each telling a different story about your journey. In the vast expanse of space, a comet streaks across the cosmos. Speed is the measure of its progress, the rate at which it covers distance. But to truly understand the comet's journey, we need velocity. Velocity speaks of both speed and direction. Imagine two cars racing down a track, both with identical speedometers. While both cars may possess the same speed, their velocities tell a different story. We often think of motion as a steady state, a constant speed. But the universe thrives on change. It's here that we meet acceleration, the rate at which velocity changes over time. Imagine a rocket launching into space, its velocity increasing rapidly. Positive acceleration indicates an increase in velocity, like our rocket ascending. Negative acceleration or deceleration implies a decrease in velocity, like a car braking to a stop. For centuries, mathematicians and physicists have strived to capture the elegance of motion in the language of mathematics. Enter the equations of motion, formulas that describe uniformly accelerated motion. These equations are powerful tools that allow us to predict and understand the motion of objects with remarkable precision. With these equations, we can calculate the distance traveled by a speeding car or the final velocity of a rocket as it escapes Earth's gravitational pull. In the year 1687, Sir Isaac Newton gifted the world with his groundbreaking work, Philosophiae Naturalis Principia Mathematica. Within its pages lay three fundamental laws that would forever change our understanding of motion and the universe itself. Newton's first law of motion, the law of inertia, states that an object at rest will remain at rest, and an object in motion will continue in motion at a constant velocity unless acted upon by a net external force. This law speaks to the inherent tendency of objects to resist changes in their state of motion. The second law provides a mathematical framework for understanding how forces influence motion. It states that the acceleration of an object is directly proportional to the net force acting on it and inversely proportional to its mass. Finally, the third law elegantly summarizes the principle of action and reaction. For every action, there is an equal and opposite reaction. Look up at the night sky and observe the celestial ballet of planets orbiting their stars. This is circular motion, a mesmerizing dance governed by centripetal force. Imagine swinging a ball tied to a string in a circle. The string constantly pulls the ball towards the center, preventing it from flying off in a straight line. Without centripetal force, circular motion would be impossible. Imagine the graceful arc of a basketball soaring towards the hoop. This is projectile motion, a blend of horizontal and vertical motion under the influence of gravity. Picture a cannon firing a ball horizontally from a cliff. Gravity acts as an invisible hand, constantly tugging the ball downwards, bending its trajectory into a parabolic path. In the vast expanse of the cosmos, stars, planets, and galaxies engage in a delicate gravitational ballet. This cosmic dance is orchestrated by gravity, one of the fundamental forces of nature. Sir Isaac Newton unveiled the law of universal gravitation, a profound insight into the force that binds the universe together. Newton's law states that every particle in the universe attracts every other particle with a force proportional to the product of their masses, and inversely proportional to the square of the distance between their centers. Gravity, despite being the weakest of the fundamental forces, reigns supreme on the astronomical scale, shaping the large-scale structure of the universe. From the falling of an apple to the intricate movements of galaxies, motion underpins the very essence of our universe. Understanding its principles has driven scientific advancements and revolutionized our world through engineering marvels and technological innovations. As we conclude this exploration of motion, let us remember that we are part of a universe in perpetual dance, a cosmic ballet where every object is engaged in a delicate interplay of forces.